Okay, so a psychologist claims that the color blue has a calming effect. And to verify the claim, he recorded heart rates from patients before and after showing a blue screen. The data is shown below, before values, after values. What do you think? Do you think that it has a calming effect just by looking at the data? Huh?
Yeah.
Just sort of, okay. So we'll see. Before minus after. Typically, I said, last time, we'll do post minus three. Now, because of Gunnar, we'll blame him. The nature of this test or nature of this data, if I did post minus 3, it will end up, with a left tail test. Yes, but we did a left tail test last time. So I want to do a right tail test. So I'm going to define it as before minus after. Good. Okay. The first case, the difference 72 minus 72 would be 0. 87 minus 81, 6. 70 minus 72, negative 2. 68 minus 70, negative 2. 121 minus 71, 51. 101 minus 81, 20. 134 minus 92, 42. Good. We have identical before and after, which makes that magnitude 0. What did I say when I went over Wilcoxon sign rank? Anytime you encounter a difference of 0, what do?
We can remove it.
We have to remove it. So we're not going to look at that. So the sign, this is 1, 0, 0, 1, 1, 1. Which statistic do we always use? Do we use T plus or T minus? I mean, in practice, it doesn't matter. But your book sticks to one thing. What is that one thing? Keeping T plus. Okay. So the absolute value here, 6, 2, 2, 51, 20, 42. Good. Now we want to assign ranks. Well, the lowest would be here. So I've got 1, I've got 2. This is a problem where we have zeros and we have ties. Yes. So anytime you have a tie, you take the average of the ranks. If it were different. Well, if these two were different, what would be your rank? Hypothetically, if these were different, what ranks would you assign?
Rank 1 would go to the lowest.
Okay, rank 1 would go to the lowest, the next one has to be 2, right? But since those two are the same, I'm going to average them and assign a rank of 1.5. Yes, so 1.5 here, 1.5 there. And the rest I'm going to assign starting at 3 because I averaged 1 and 2. The next rank would be 3, 4, 5, and 6. Yes.
Yesterday we did, or not yesterday, last class we did the post minus pre, and now we're doing the pre minus post, basically. Is why are we doing that?
Because it's gone. Because last time, if I defined this problem as post minus 3, I would have ended up, or the reasonable thing would be to test for a left tail test. Or you do a left tail test. I don't want to because we did it last time.
Okay.
So I changed it so that we can do a right tail.
Okay.
So by all means, we just have to add the sum of positive rungs, which is the same as saying, I multiply psi I with Ri, so 1 times 3, 3, 0, 0, 6, 4, 5. Good. Add them all together. 6 plus 3, 9, 9 plus 4, 13, 13 plus 5, 18. So when I multiply psi I with Ri, in effect, all I'm doing is summing the positive numbers. So that happens to be 18. So T plus is 18, yes. I'm just finding adding the positive rungs. Those are the ones with positive rungs. Do you agree? That one, that one, that one, and that one. Yes. It is equivalent to saying I multiply 1 times 3. Since negative ranks are assigned 0, they'll all be excluded. Yeah, I just wanted to show you as to why we assign 1 and 0. As I mentioned last time, you could also do 1 and minus 1. We're not going to do that here. If we did not have any ties, then this would be great. But unfortunately, we have ties. So when we have ties, we want to identify the number of groups with a tie. So how many groups do we have a tie with? Only one group, yes? That is one group with ties. That is good enough, but the book actually says or uses, that's the first group, calls it T1, T2, T3, T4, and T5. Yes, even though the others don't have a tie, the book takes this approach. So what does that mean? In each group, we've got to determine the number of observations that are tied. In the first group, how many do we have? Number of observations, 2. Second group, is there a tie?
No.
No. So T2, T3, T4, T5, it would all be 1. Agreed.
Yes.
Well, why should we do this? Well, just uses T star. Well, I'll just put a star here. Now, T star will not change. In other words, even with the ties, we can keep it at 18. Now, where do these come into play? The lowercase t's play a role in the large sample approximation, which I'm going to do today. So before we get to that, how did we reject or not reject the null? With Wilcoxon, we wanted to find the critical value. Yes. How did we find the critical value last time? So last time it was Q signed round. That will give us the percentile corresponding to the critical value. Alpha, in this case, is 0.01. So Where should the rejection region be? The left-hand side or right-hand side? This is a right tail test. What is our definition? The null is that theta is 0. Alternative, theta is bigger than 0. In other words, the before values are bigger than the after values, indicating that the heart rate was higher before compared to after. So we are looking at a right tail test, and we want to find that critical value, t plus lowercase alpha. I said that when it comes to Q rank, we always enter the area below the critical value. This is a right tail test, and alpha is 0.01. And if alpha is 0.01, which is the area above, how do we find the area below? Its complement, which is 1 minus the alpha that we have. So 1 minus 0.01. We're going to keep alpha as is. And we have to specify n. What is n? Is n 6 or is it 7? 6. Originally, we have 7 observations, but we got rid of 1, so n is 6. I end up getting 21. Good. So the rejection region starts at 21 and above. Where does the test statistic fall?
18.
18, somewhere right here. We reject in a right tail test if t plus is bigger than or equal to the critical value on the right hand side. Yes. Is it bigger than or equal to the critical value? No. The critical value is 21. The test statistic is 18. Clearly, 18 does not exceed 21. So our conclusion, t plus is less than 21, which would imply do not reject null. If we do not reject null, our conclusion is that theta equals 0. Theta goes back to the definition of z. Our definition is before minus after equal to 0. Yes, which would imply before is equal to after. Correct? If the heart rate before looking at the screen and after looking at the screen are one and the same, do you believe that blue is a common color? No. So this would imply blue is not common. So even though it sort of looked like it, but it actually isn't. So the next step would be to find the p-value. So to find the p-value, we have to use p sign, right? And this is a right tail test, so the p-value is the area above the test statistic. By default, R is going to look at or give you the area below. That's just how it is. Unless you turn on that lower dot tail to be equal to false. I don't want to confuse you with all that. So the test statistic is 18 and n is 6. When I do that, I'm going to get the area below because that is the default. So I end up getting 0.953125, but I want to find the area above. So 1 minus 0.9531 gives me 0.0469. Is that bigger than 1%? Alfred, yes.
So you value always area below. Because you had to do 1 minus.
Not the p value. What R gives you will always be below. But in this problem, it's area above the test statistic, so we've got to take a complement. Here is a question we rejected because I set an alpha of 0.01, correct? Had I set it as 0.05, would I reject? No. So this is a borderline case. Do you agree? So the only reason why we rejected is because of my strict condition about alpha. But if alpha is 0.05, my conclusion would be different. I would have concluded that blue is in fact calming, which sort of agrees with our initial thought by looking at the data, correct? So this is definitely a borderline case. So what should the psychologist do? Perhaps look at a few more patients, right? Readjust the sample and see, maybe it is in fact a common color. Are we clear?
Yeah.
Yes. Okay. I need. So we could do a large sample approximation. I am going to assume that the large sample approximation is valid for in this case. In practice, I will stop right here, where we concluded, because that's it. Purpose of doing a Wilcoxon sign round test is because our sample size is small and we are doing it in a distribution-free manner. But if I assume that large sample is going to work, then we need the mean and the variance to find a standardized test statistic, which is a z-score. The mean is always n times n plus 1 over 4. The variance of the test statistic under the law is n times n plus 1 times 2n plus 1 over 24 minus so n times n plus 1 times 2n plus 1 over 24 minus this giant sum. Looks complicated, but in reality it's not. This adjustment will only matter when you have a time. And earlier I mentioned we don't have to do this. We just have to look at the groups that are tied. The reason being, all of these groups do not have a tie. So I have to in total 5 of them. So if G is 5, I'm going to sum all the values starting from 1 through 5, plugging the TI values. But when I have I equals 2, 3, 4, and 5, they all have only one observation in there, correct? 1 minus 1, 0. Does that make sense? So anytime you don't have a tie, it simply means no matter what I you pick, Ti will always be 1, which would make this entire term go away. So you just have that. Does that make sense? So this adjustment comes into play with the variance only when you have a tie. So of all the groups that we have 5 of them. The only one that is going to get a non-zero value is I equals 1. Do you agree? Yes. So what is the mean? N is 6 times 6 plus 1 over 4. 2, 3, 7 times 14 over 3. Yes, which is 4.67 approximately. All I did is I plugged in n is equal to 6 in the formula. 6 times 6 plus 1 over 4. 6 plus 1, 7. I cancel those 2. I get 14 over 3. Good. I don't need these anymore, so I can erase all of that. Variance is sigma squared, not the standard deviation, this is the variance. Plug it in the formula, 6 times 6 plus 1. 6 times 2, 12 plus 1, divided by 24, minus 1/2. There is only one tie group, and that is an I equals 1. With me? Every other group doesn't have a tie, it means it has only one observation. 1 minus 1 would become 0. So minus 1/2, the number of ties in the group, so T1, 2, T1 minus 1, 2 minus 1, 2 plus 1. Yes? So let's see. 6 times 7 times 13 over 24. Minus 1/2 times 2 times 3. 91 over 4 minus 3. Yes? 22.7. Blame it on a Monday. 19. 19.75 minus 3, I end up getting 16.
Well, no, that's with the minus three.
I was right. What is 19? It's 22.7, correct?
Yeah,
I guess, yeah. that-
0.75.
Trying to ruin my day. So approximately 19.7. Yes. It's not the variance that we're going to use in the z-score, it's the standard deviation. So t plus minus mu divided by sigma. Sigma would, yes.
Calculating the mean, why is the 2 on top of the 3 on the bottom?
I got 10.5 by the way. for that.
For the mean,
Yeah, I got
So they give you
10.5.
the-
n is 6, right?
Yep.
Oh, 2 times 3. Oh, I have it backwards. Thank you. What is it?
I got 10.5.
10.5, bad math. I'll blame it on a Monday again. What is sigma? Sigma is square root of 19.7. If you see something wrong, let me know, don't wait till the very last minute. And everything would be wrong. 4 point something, yes? 4.45. So 4.44. Okay, now over here, T plot is 18 minus 10.9 or 10.5 divided by 4.44, which is 7.5 over 4.44. What do we get? 689. Good. Now, there are two ways to come to a conclusion, the large sample approximation, finding the p-value, finding the critical value. Since this is a large sample approximation, the distribution is normal, just like we've done before. And how did we find the critical values for a normal distribution? You will know if you did the homework. So we have to use inverse norm, second vars, number 3. Mind you, inverse norm, just like R, will always use the area below the critical value, always. But in this case, we have to look at the area above. The area above is our alpha, which is 0.01. If the area above is alpha, what is the area below? .99.
You just take 1 minus.
Exactly. So 1 minus 0.99. The calculator will assume that the mean is 0, standard deviation is 1. Enter. I get negative 2.326. So that is the area below 0.01. Since I did 1 minus already, I'm doing it twice. So if the area above is 0.01, area below is simply 0.99. And you can see that 1 is the positive of the other. So even if you find one of them on the left-hand tail, you can multiply by -1, get the one on the right. So the critical value happens to be 2.33. Now, where is the test statistic? 0 is in the middle. Did the test statistic fall in the rejection region? No. So anything above 2.33 is the rejection region. The test statistic falls at 1.689, which would imply do not reject. No. Same conclusion. What about the p-value?